Hello everyone, so today I'm going to be sharing with you a video presentation which is a requirement in our course Math Analysis for Teachers with Dr. Jess Pizarro. In this video, I'm going to be sharing with you some theorems on continuity and their application. By the way, I am Mrs. Stephanie B. Palakay, a student of the Graduate School of St. Paul University, Philippines under the program Master of Science in Teaching Mathematics. Okay, so let us start. But before we go to the different theorems on continuity, first, let us define what is continuity. To better understand its definition, let me show you a scenario which can be likened to that of the definition or concept of continuity of functions. So we have here on the screen an illustration of two water pipes. So we have here water pipe 1 and water pipe 2. Now look at water pipe 1. As you can see in the illustration, it is composed of three parts joined together. So we have this part, and then the second part, and then the third or the last part. And then these parts are joined together so that if we will let water run through this pipe or in pipe 1, and we can see that water will run through continuously from the first part of the water pipe 1 down to its third part. Now the question is, will the water from pipe 1 run through continuously to pipe 2? So the answer is definitely no, because there is a gap between water pipe 1 and water pipe 2. Okay, so there would be a discontinuity in the flow of the water from pipe 1 to pipe 2. Now, only after these two pipes are joined together will the water run through continuously from water pipe 1 down to water pipe 2, because there is no longer a gap between the two water pipes. Now, how can this scenario be connected, or how can this scenario be in relationship with the concept of continuity of functions? Now let us study the definition of continuity of functions. A function f of x is said to be continuous at x is equal to a if and only if the limit of f of x as x approaches a is equal to f of a, which means the limit of the function as x approaches a should be equal to the value of the function at x is equal to a. Also, a function is said to be continuous on the interval a, b if it is continuous at each point in the interval. Okay, so if we would graph the function and try to trace its graph using a pencil, there would be a smooth transition from point A down to point B. So we will not be lifting our pencil as we are tracing the graph of the function from point A to point B, which means there is no gap in the graph of the function. So this can be likened to the scenario of the two water pipes joined together, wherein the water had flown smoothly or continuously from water pipe 1 down to water pipe 2 because there is no longer a gap between the two pipes. So from our definition of continuous functions, we can draw three important things to take into considerations. First, the function must be defined at x is equal to a, which means f of a must exist. Second, the limit of the function must exist as x approaches a. And lastly, which is the most important, these two values must be equal. So the limit of f of x as x approaches a should be equal to f of a, or the value of the function at x is equal to a. Otherwise, if these two values are not equal, then the function will be discontinuous as at x is equal to a. Let us try to study the graph of this function, and then let us determine whether the function is continuous at x is equal to -2, x is equal to 0, and x is equal to +3. So to answer this, we have to evaluate the value of the function at each point and the limit of the function as it approaches each point, and then let us try to compare these two values. If the two values are equal, then the function is continuous at that point. Otherwise, if the two values are not equal, then the function is discontinuous at that point. Now let us start with x is equal to negative 2. So first, let us evaluate the value of the function at x is equal to negative 2, or that is f of negative 2, which is equal to positive 2. So we can get that in this part of the graph. And then next is to find for the limit of the function as x approaches negative 2, which is undefined. Why undefined? Because the left hand limit and the right hand limit do not tend to meet each other, or they are not equal. That's why the limit of f of x as x approaches negative 2 is undefined. And we can see here that the two values are not equal. Therefore, the function is discontinuous at x is equal to negative 2. Okay, this type of discontinuity is what we call the jump discontinuity. Okay, this happens when there is a break in the graph of the function, just like what happened in this graph of the function at x is equal to negative 2. Next is at x is equal to 0. So again, we have to evaluate the value of the function at x is equal to 0, or that is f of 0, which is equal to 1. So we can find it here. And then secondly, the limit of the function as x approaches 0, which is also equal to 1. Okay, so the right hand limit and the left hand limit tend to meet each other at point 1. And we can see that the two values are equal. That's why the function is continuous at x is equal to 0. And then lastly, at x is equal to 3, again, let us evaluate f of 3, which is negative 1. So this is the value of the function at x is equal to 3. And then the limit of the function as x approaches positive 3 is 0. So although the value of the function is negative 1 at x is equal to 3, but the right hand limit and the left hand limit meet at point 0. That's why the limit of the function as x approaches 3 is equal to 0. And again, these two values are not equal. Therefore, the function is discontinuous at x is equal to 3. Now, this type of discontinuity is what we call the removable discontinuity. This happens when there is a hole in the graph of the function. So from this example, we can get a quick working definition of continuity of functions. So we can say that a function is continuous if there are no holes in its graph or there are no breaks in its graph. In this case, in our example, this function has two discontinuities. Okay, it is discontinuous at x is equal to negative 2 and x is equal to 3. Now that we already have a clearer view on the concept of continuity, let us now proceed on the different theorems on continuity. First, we have all polynomial functions and the functions sine x, cosine x, arctangent x, and e raised to x or exponentials are continuous on the interval negative infinity to positive infinity. This means that these functions are continuous everywhere, or these functions are continuous at all values of x. Now, let us take a look at the graph of these functions. So, for the colored red, we have the sine function, blue for the cosine, green for the arctangent, and purple for the exponentials. So, as you can see, this verifies theorem number 1. No matter how we extend their graphs on both sides, so on positive infinity and negative infinity, we will not be able to find any hole or break in their graphs. That means these functions are continuous everywhere. Now we are going to have this example as an application of theorem number 1. So we are going to evaluate the following limits. First, the limit of sine x as x approaches 0. Second, the limit of cosine x as x approaches pi. And third, the limit of arctangent x as x approaches -1. So first, we have the limit of sine x as x approaches 0. So sine x is a function which is continuous everywhere, that is based on theorem number 1. So we are sure that a limit exists as x approaches 0. So what we have to do is just to substitute 0 at the function. So we now have the limit of sine x as x approaches 0 is equal to sine 0, which is equal to 0. So the value of the limit of sine x as x approaches 0 is equal to 0. So if we try to graph this function, we can see that as x approaches 0, f of x also gets closer and closer to 0. So it is very evident that the limit of the function is equal to 0. Second, we have the limit of cosine x as x approaches pi. So just like our first example, cosine x is also a function which is continuous everywhere. That is also based on theorem number 1. And we are also sure that a limit for cosine x as x approaches pi does exist. Okay, so we just substitute pi on the given function. So that is the limit of cosine x as x approaches pi is equal to cosine pi, which is equal to 1. Therefore, the limit of cosine x as x approaches pi is equal to 1. So for the last item in our example, which is the limit of arctangent x as x approaches -1, I will leave that to you to work on. And to verify your answer, you can just scan this code using a QR code scanner. Now let's move to the second theorem, which states that if functions f and g are continuous at x is equal to a, then their sum, which is f plus g, is continuous at x is equal to a. Their difference, which is f minus g, is continuous at x is equal to a. Their product, f times g, is continuous at x is equal to a, and their quotient, f divided by g, is continuous at x is equal to a if g of a is not equal to 0. But if g of a is equal to 0, then f divided by g is discontinuous at x is equal to a. This theorem is a direct result of limit laws. For example, to show that f of x plus g of x or f plus g is continuous at x is equal to a, we have to prove that the limit of f of x plus g of x as x approaches a is equal to f of a plus g of a. Now in our proof, first we have to establish that the limit of f of x is x approaches a is equal to f of a. And the limit of g of x as x approaches a is equal to g of a. This is because it is given that these two functions are continuous. Then, we now have the limit of f of x plus g of x as x approaches a is equal to the limit of f of x as x approaches a plus the limit of g of x as x approaches a. Okay, this is applying our limit laws. This is the limit of the sum of two functions. Now we have the limit of f of x plus g of x as x approaches a is equal to f of a plus g of a. Okay, that is by substituting limit of f of x as x approaches a by f of a, since this is continuous, and limit of g of x as x approaches a by g of a, since it is also continuous. As an application of theorem number 2, let us work on this example. Let f of x be equal to sine x and g of x be equal to x squared minus 4. Where are the following functions f plus g, f minus g, f times g, and f divided by g continuous? So we have our first function, which is sine x, and second function as x squared minus 4. Sine x is a continuous function based on theorem number 1, so it is continuous everywhere. And then x squared minus 4 is a polynomial function, specifically a quadratic function, which is also continuous everywhere based on theorem number 1. So we have f of x and g of x as continuous functions everywhere. Now we can have these conclusions. First, their sum, which is f plus g, is also continuous everywhere. Second, their difference, which is f minus g, is also continuous everywhere. Third, their product, which is f times g, is also continuous everywhere. But for their quotient, which is f divided by g, it is continuous everywhere except for the values of x, wherein we could have g of x equal to 0. So if g of x becomes 0, then the function is discontinuous at those values of x. These values of x for which the denominator g of x becomes 0 can be solved by finding the zeros of this polynomial function. So we have x squared minus 4 is equal to 0. As you can see, this function is a difference of two squares. We have x squared and 4. So we can factor this as the sum and difference of two terms. So for the first term we have x, the second term is 2. Now we can use these factors to solve for the values of x, by which g of x becomes 0. So we have x is equal to negative 2 and x is equal to positive 2. So the function f divided by g is discontinuous at x is equal to negative 2 and x is equal to positive 2. Now let us proceed to theorem number 3, which states that a rational function is continuous everywhere except at the values of x that make the denominator of the function equal to 0. This is somewhat similar to the quotient of two continuous functions, only that in this theorem we are dealing with rational functions. Let us apply theorem number 3 in this example. Find the values of x at which the function f is discontinuous. So the given function is f of x is equal to x plus 4 all over cosine x. Okay, rational functions are continuous everywhere except where we have division by 0. So to find where this function is discontinuous at, we have to determine the values of x that makes the denominator equal to 0. So to do that, we have to equate the denominator to 0 and find for the values of x that makes it 0. So that is cosine x is equal to 0. Okay, the values of x that makes cosine x equal to 0 is given by x is equal to pi over 2 plus k times pi, where k is any integer. Therefore, the function f is discontinuous at x is equal to pi over 2 plus k over pi. So these are all the values of x that makes the denominator equal to 0. So the function is discontinuous everywhere except for the values of x, which is equal to pi over 2 plus k times pi. So discontinuities on rational functions can be similarly solved in this manner. We just have to find for the values that makes the denominator equal to 0, and these are the values where the function will be discontinuous at. So for our fourth theorem, it states that if the limit of g of x as x approaches a is equal to L, and if f is a continuous function at x is equal to L, then the limit of f of g of x as x approaches a is equal to f of the limit of g of x as x approaches a, or f of L. So we have two functions here again. We have g of x whose limit is defined as x approaches a, which is equal to L, and the function f, which is a continuous function at x is equal to L. Again, let us apply theorem number 4 as we evaluate the limit of sine 2x plus 5 as x approaches a. Okay, as you can see in our example, we have two functions here. we have the f of x, which is the sine function, and the g of x as 2x plus 5, or the polynomial function. And since sine x is a continuous function everywhere, and 2x plus 5, which is a polynomial function, is also continuous everywhere, then we can have the limit of sine of 2x plus 5 as x approaches a is equal to the sine of the limit of 2x plus 5 as x approaches a, which is equal to the sine of 2a plus 5. So as you can see, we have brought out the sine function from the limit, and then we just evaluated 2x plus 5 by substituting x by a, and that is equal to sine 2a plus 5. Next, for theorem number 5, we have if g is a continuous function at x is equal to a, and function f is continuous at g of a, then the composition f of g is continuous at x is equal to a. So this theorem focuses on the composition of two functions f and g. Now let us apply this theorem as we solve this problem. We have to show that any function of the form e raised to ax plus b is continuous everywhere, where a and b are real numbers. Okay, so the function in our example is an exponential of the form e raised to x and is a function that is continuous everywhere. And then we have our g of x, the second function, ax plus b, which is a polynomial or a linear function, which is also continuous everywhere. So our function e raised to ax plus b is the composition of f of g of x. So since both of the functions f of g and g of x are continuous everywhere, therefore the composition f of g of x is equal to e raised to ax plus b is also continuous everywhere. Finally, we have theorem number 6, which is called the intermediate value theorem, which states that suppose that f of x is continuous on the interval ab, and let m be any number between f of a and f of b, then there exists a number c such that c is greater than a but lesser than b, and f of c is equal to m. So what the intermediate value theorem is really saying is that a continuous function will take on all values between f of a and f of b. So this one is a graph of a continuous function which illustrates the intermediate value theorem. As we can see from this image, if we pick any value m that is between the value of f of a and the value of f of b and draw a line straight out from this point, the line will hit the graph in at least one point. In other words, somewhere between a and b, the function will take on the value of m. Also, as the figure shows, the function may take on the value at more than one place. It is also important to note that the intermediate value theorem only says that the function will take on the value of m somewhere between a and b. It doesn't say just what the value will be. It only says that it exists. So the intermediate value theorem tells us that a function will take the value of m somewhere between a and b, but it doesn't tell us where it will take the value, nor does it tell us how many times it will take the value. These are important ideas to remember about the intermediate value theorem. A nice use of the intermediate value theorem is to prove the existence of roots of equations, as the following example shows. In this example, we have to show that p of x is equal to 2x cubed minus 5x squared minus 10x plus 5 has a root somewhere in the interval -1, +2. So what we are asking here is whether or not the function take on the value p of x is equal to 0 somewhere between -1 and -2. Or in other words, we want to show that there is a number c such that c is in between -1 and +2. And to show that, first, let us define m be equal to 0, a is equal to -1, and b is equal to 2. So this problem is set up to apply the intermediate value theorem. So all we have to do is to show or prove the following. First, the function is continuous. And then second, that m is equal to 0 is between p of -1 and p of 2. Or that is 0 is greater than p of -1 but lesser than p of 2, or p of 2 is lesser than 0 and 0 is lesser than p of -1, so that we can say that a number c exists such that this number is in between -1 and +2. To do this, all we have to do is compute. So we are going to compute for the values of p of -1 and p of +2. So evaluating p of -1 in the function p of x is equal to 2x cubed minus 5x squared minus 10x plus 5, we can have the value of p of -1 equal to 8. And for the value of p of 2, we have -19. With this, we have already satisfied our second condition that m is equal to 0 must be in between p of -1 and p of 2, and that is 0 is greater than p of 2 but lesser than p of -1, or 0 is greater than -19 but lesser than +8. We have also satisfied our first condition, which states that the function must be continuous. Since our function is a polynomial function, and Theorem 1 states that all polynomial functions are continuous everywhere. So, by the intermediate value theorem, we have there exists a number c such that c is in between -1 and +2, which gives us the value of the function equal to 0. Therefore, the polynomial has a root somewhere between -1 and +2. Take note that the intermediate value theorem only says that there exists a root between -1 and +2. It does not tell us what value would it be. Okay, so it only proves the existence of a number c, but it does not tell us the value of c. So for the sake of completeness, this shows the graph of the function p of x on the interval -1, +2, showing that a number c really exists that give us the value of the function p of c equal to 0. Take note that the value here, which is 0.4250308563, is not given by the intermediate value theorem, but a computer program had helped us to evaluate the value of c. So the intermediate value theorem had only helped us prove that value c exists somewhere in between -1 and +2. And with that, I will leave you this problem to work on using the intermediate value theorem. Determine whether the function f of x is equal to 20 sine x plus 3 times cosine x squared over 2 takes on the value f of x is equal to 10 in the interval 0, 5. Again, to verify your answer, you can just scan this code using a QR code scanner. Thank you for watching this presentation, and I hope you will find it useful in dealing with limits and continuity. Happy learning and stay safe, everyone.